We are now going to take advantage of what we've learned about logarithms to help us solve equations where the unknown is in the exponent. For example, in this equation, 4 raised to the x equals 13. The unknown x is part of the exponent, and in order to isolate x, it turns out we're going to want to use one of the properties of logarithms we've studied. So, in particular, we're going to use the property that allows us to imagine we're taking an exponent and moving it out front to change this into just multiplication. So this property works for any base logarithm. And in this problem, let's apply it with base 10, the common logarithm, so that we don't have to do any extra work on a calculator when we're ready to evaluate our final answer. So we start by taking the logarithm of both sides, base 10 common logarithm, and that allows us to move the exponent out front. And now we have x times a number. Remember, log of 4 is just a number. We could evaluate that on our calculator to get a decimal approximation if we wanted. So this is x times something. To isolate x, all we have to do is divide by this quantity. So we'll divide both sides by log of 4. That isolates x, giving us log of 13 divided by log of 4. So that's the exact answer. And if we want a decimal approximation, we can type this into our calculator. And if we do so, we'll get approximately 1.85. So that's it. That's the x value. This is the exact value, and this is an approximation of it that you plug in to make this equation true. Let's try another example. This one's just slightly more complicated. So this time we have 2 times something raised to a variable equals 25. So the first step we want to take is to divide both sides by 2. What that will achieve is giving us something that looks like the previous example, where we have a number raised to the variable. The next step will then be to apply property of logarithms again. So we're going to take the logarithm of both sides, allowing us to bring the exponent out front, changing this into multiplication now. So we brought the exponent t out front, giving us t times log of 1.02. And then to isolate t, we'll divide both sides by that number, log of 1.02. So we have the log of 12.5, which was on the right side, divided by log of 1.02, which had been multiplying t on the left side until we moved it over. This is the exact value, and then plugging that into a calculator to produce a decimal approximation gives us approximately 3.64. Here's another example. This time the exponent is a little bit more complicated. The exponent is not just a variable, but it's an expression involving the variable. It turns out we can approach this in more or less the same way. If you think about the order of operations on the left side, if you plugged in a value of x, first thing you would do is multiply it by 2. Then you would add this 1 to it. That would give you a number, and once you knew that number, you could raise 4 to that power. And after you did all that, the last thing you would do is multiply it by 6. So in order to isolate x, we're going to reverse the order of those steps. So the first thing we'll reverse is the multiplying by 6. That means the first step in our algebra is to divide both sides by 6. Then we want to undo this exponentiation, and to do that we're going to apply logarithms so that we can bring the exponent out front. So again, let's take a common log of both sides. That allows us to bring the exponent out front, and now this time the exponent is this entire expression, 2x plus 1. That whole thing has to come out front of the logarithm. So now there's a little bit more work to do to isolate x, and this is an algebra problem now. Just remember, log of 4 is a number. Maybe it's 0.1 or 0.2 or something like that. You want to imagine that it's just a number and apply the same algebraic steps you would take if you saw a whole number here. So the first thing you should do is move this to the other side by using division. And then to further get the x by itself, we'll take this plus 1 and move it by subtracting 1 from both sides. And then finally, we'll divide both sides by 2. So this is the quantity that was on the right side, and then it gets divided by 2. This is the exact value of x that satisfies the equation, and if you type all that into your calculator carefully, you can get a decimal approximation of about 0.91. Let's do one more. This time we have 2 times e to the x equals 30, and remember e is that special number. It's approximately 2.71828. Now, it's not exactly this, it's just approximately this, and we'll see later in the course where that number comes from. Our first step will be just as before. We'll start by dividing both sides of this equation by 2, giving us just e to the x equals 15. Now, I could use a common logarithm here like in the previous examples, but actually whenever we see a base of e, it's a good idea to use the natural logarithm, and we'll see in a moment why. So let's take a natural logarithm of both sides. Remember, natural log just means log base e. Now we can bring the exponent out front. And your next thought would probably be to divide both sides by natural log of e, and that is valid, but it's actually unnecessary, because natural log of e, this is really equal to 1. Remember that natural log means log base e. And so log base e of e means what power of e do you need to get e? And of course the answer is you want a power of 1. So that's where this value comes from, which means this quantity is just equal to 1. And so if I simplify, x times 1 is just x. So this is the exact value, natural log of 15, and evaluating that on a calculator gives you a decimal approximation of about 2.7.